So this is a picture of Mount St. Helens, which is actually in the same volcanic chain as Mount Rainier where we started this PowerPoint. Mount St. Helens is a fantastic example of plate tectonics in action. It erupted in 1980 after several months of a predicted eruption. And what's cool about it is that it didn't erupt out of the top of the cone-shaped volcano. A bulge grew along the northern flank of Mount St. Helens, and it actually erupted out of the side. This photo was taken on an area called Johnston Ridge. Johnston Ridge is named after a geologist named Johnston who actually died in the eruption of Mount St. Helens as he hovered over the lava dome in a helicopter. And his last words were, "I think this is it," and he was right. So again, all these volcanoes that we've been talking about exist because of plate tectonics. Plate tectonics is the idea that the crust of the earth is actually broken into plates. And I encourage you to watch the hyperlink here under the word plates. It's produced by IRIS, which is a branch of, it's associated with the U.S. Geological Survey. It focuses on their earthquake data. And it's a longer video, but it really illustrates what happens very nicely in plate tectonics. And especially it talks specifically about how ocean plates differ in really important ways from continental plates, and how ocean plates that are far from mid-ocean ridges, which we'll talk about in just a second, how they vary in really important ways when compared to ocean plates that are very close to the mid-ocean ridge and very young. So please watch that video. It's very good and it's very informative. So these plates on the earth, as part of the crust, are broken sort of along mountain ranges, along ocean ridges, and along continental and oceanic boundaries. You'll learn a little bit more about this in every chapter really of this semester. So the plates are always in motion, even though occasionally they'll get stuck and locked for a bit, but regardless, they interact with each other in three different ways, and these are called plate boundaries or plate margins, we're going to talk about them for the next few minutes. So one of the ways that plates interact is actually by moving further away from each other. That's called a divergent boundary. So if you think about the word divergent or diverge, it means when things are moving apart, and that is exactly what's happening in divergent plate boundaries. The majority of divergent plate boundaries are actually found in the ocean. So if you look here, here is the island of Iceland, and it is the surface expression for this very long feature called the mid-ocean ridge system. And that goes right down the Atlantic Ocean. It connects with another segment of mid-ocean ridge system around in the Southern Ocean, goes up into the Indian Ocean, and because the world is round, you're going to have to bear with me here. It wraps around here into the Pacific Ocean, and is the largest physical feature on, the longest, I should say, physical feature on Earth. It's over 42,000 miles long. And what's really cool is it was discovered in like the 1960s. So I think that's amazing that one of the biggest things on the Earth we didn't even know about more than about 50 or 60 years ago. So watch the video up here that is hyperlinked to the word apart, because that video will walk you through, again, this is from the U.S. Geological Survey, which is a branch of the Department of the Interior in the U.S. government, and it illustrates very simply how plates move apart and what happens at mid-ocean ridges, where the crust of the earth is literally being torn apart. So at this ridge, everything to the left is being pulled to the left, and everything to the right is being pulled to the right. I like to think about divergent plate boundaries as places where the crust is so thin that it causes melting right beneath the surface of the crust and the upper mantle. And I tell my students very often, because it's sort of a memorable image, to think of this as almost like having a bad cut on your arm. And where this rift is at this divergent boundary, what's basically happening is this cut in the earth is being pulled apart. And what happens then is that lava really rises up here to fill in the gap. And that lava is hot, and because it's hot, it's very thick. It's kind of like when you first take a cake out of the oven, the way it is sort of puffy, if you will. So right along these mid-ocean ridges, the basalt, which is the type of rock that comes up here, is very thick and it's very buoyant, and it pushes the crust upwards here. It makes it extra thick right along the mid-ocean ridge. And then as it's pulled further away, what you see in the video is that it cools off and it gets older and it starts to sink a little bit. So most of these divergent plate boundaries where plates are moving apart are located in the oceans. There are some that are on land, and we'll talk about a couple of those later this semester. The second type of way that plates can interact is at what's called a convergent plate boundary. And again, follow the link here, the hyperlink under boundary. It goes to a fun video where you can actually see not only what happens at convergent plate boundaries, but you also see how it's related to earthquakes and tsunamis, which are intricately connected at this sort of an environment. So if I had like one diagram that really summed up a lot of physical geology, it would actually be this diagram. So here we have some oceanic crust that is subducting in what's called a subduction zone beneath continental crust. This is exactly how Mount Rainier and Mount St. Helens are created. There's oceanic crust off the west coast of the United States near Oregon and Washington State and a little bit of Northern California. And because the ocean crust is heavier and denser, when it collides with the North American continent, it sinks. When it sinks at the subduction zone, a couple things happen. First of all, it drags some of the crust down a little bit and it creates a very deep, narrow area called an ocean trench. The deepest parts of the ocean are above these ocean trenches. And as that oceanic crust is dragged down into the upper mantle, it starts to melt. And when it melts, it creates magma. The magma rises up through the crust and it can erupt at the surface in a chain of volcanoes. So again, plates are colliding, and you can tell that from these blue arrows here. And the denser one, tends to sink and melts and creates magma that can erupt as lava at convergent plate boundaries where plates are colliding again. Okay. All right. Our last type of plate boundary is where plates are sliding past one another. And you can watch a short video clip here about transform boundaries. The most famous transform boundary in Earth is the San Andreas Fault. So this is really famous for several reasons. And honestly, this is much more complicated than this particular diagram makes it out to be. There's a lot of segments of the San Andreas Fault. It behaves differently in different places. But regardless, what you see here is that the arrows right near Hollister in California illustrate that this part of California is moving to the northwest and this part is moving to the southeast. And this is where our transform plate boundary is, where they're sliding past one another. So you can see that this cuts through major population centers. And that's one of the reasons that this is one of the most well-studied fault systems on the earth. If you look, San Diego, California is down here, Los Angeles, San Francisco, huge population centers, very wealthy part of the country. Most of the fruit in our country is actually grown here in the San Joaquin Valley. So again, very important to the United States for certain is the presence of the San Andreas Fault. So when you drive over the San Andreas Fault, you're actually driving over from one plate onto another plate. So if you were to cross near Parkfield, for example, if you were over on this side, on the east side of Parkfield, you'd be on the North American plate. And when you drove over the San Andreas Fault, which is mapped and marked, you would end up on the Pacific plate here. It's very easy for the most part, because this is a desert-like environment, to be able to actually see the fault trace right from the air. And so if you look, this stream flowed down this sort of coastal mountain, if you will. And when it hit the San Andreas Fault, the rock was pulverized because the rock has been sort of sheared apart right here. And it diverts when the plate moves, and it moves right along this crushed up rock and then continues to flow sort of downslope. So that's cool. And those are our 3 types of plate boundaries. Thanks.